Hello everyone. I'm Mohammad Salimibeni from Concordia University. This is the IoT-TD, IoT Dataset for multiple model BLE-based indoor localization and tracking paper. The development of advanced and innovative indoor localization-based services, which is called LBS, has recently become a research focal point, given increase in ongoing enthusiasm from both industry and academia on the Internet of Things and IoT concepts. One of the most critical challenges is unmet need to compute accurate dynamic estimates of the distance between sensing devices and the intended object we use via a fluctuation receive signal SREF indicator, which is called RSSI. A great number of recent approaches use additional hardware, for example, the single of array of antennas, angle of arrival AOA or angle of departure AOD, time of flight TOF, and time difference of arrival TDOA. BLE has optimized low power, optimized low power consumption, and BLE-based RSSI approaches based on RSSI approaches. RSSI values are mainly suitable for proximity localization, for example, immediate, near, or far from a place or a specific region. But BLE-based micro localization and the dynamic tracking due to the multiple fading and drastic RSSI fluctuations and other factors like the affection of the orientation are not suitable approaches in and fail to provide satisfactory results in micro localization. BLE version 5.2.1 protocol promises prosperous future of BLE-based dynamic tracking via utilization of in-phase and quadrature signals, IQ samples, for angular array processing, but this is yet to be materialized. These drawbacks have resulted in a surge of interest to develop a hybrid multimodal mixture of experts BLE-based estimation solution achieved by combining more than one tracking model like couple fingerprinting and particle filtering, integrated k-nearest neighbors, and support vector machines, combine KAN and trilateration, and other approaches, other multimodal approaches. Hybrid BLE and PR models is still in infancy. Pedestrian direction is an attractive alternative model due to the significant advancement of IMU embedded within prevalent smart handheld devices. This paper at first introduced a data set referred to as IoT-TD, which grand through consists of synchronized IMU measurements to pave the way for further reproducible research in this field, and secondly, develop a hybrid framework coupling RSSI-based tracking with PDR. Our targeted two key issues are lack of a unified data set with precise ground truth for performing BLE-based tracking in indoor environments, and concentrated focus on utilization of standalone models and lack of attention to multiple modeling in this regard. For the prepared data set, we use experimental environment, which is 3.5 to 3.5 meters area, as you can see in this figure that illustrating this environment. And 5 BLE modules are installed in this environment. As you can see in the right picture, we have 5 different BLE modules in the environment, and also 5 vacuum cameras, and also user mobile device, which is handheld user mobile device, which capture the IMU sensor data, and so the IMU sensor data and BLE and RSSI values are captured in this environment. And also we synchronously are capturing the Vicon Vera, capturing the ground truth of the user through Vicon Vera cameras. The goal is the construction of data set for potential development of multiple model solutions to fuse IMU and multi-sensor RSSI signals to more accurately localize the user within a surveillance area. The following three different tracking scenarios are implemented implemented together as values via BLE beacons, IMU measurements from the mobile device, and the ground truth trajectory via the Vicon camera. The first tracking scenarios is a rectangular walking, which a user constantly walk side of the environments in a rectangular area. The diagonal movements where the user and the target walks along diagonal of the area with constant velocity, which is the scenario second. And the third scenario is a random track where the user walks randomly inside the surveillance region. During the scenarios, all 5 BLE modules for Vicon Vera cameras and the smartphone IMU application are running and collect data, which are all saved synchronously. The rectangular and diagonal movements, scenario 1 and 2, are more rhythmic, but the third one, the random movement, is more challenging for tracking tasks. The IoT-TD dataset collect through 75 data gathering station, 25 for each of the scenarios. The ground truth, the true flight position of the user consists of 6 different components. For example, the 3-dimensional position data and the 3 rates of angular velocity, pitch, roll, and yaw are gathered and pre-processed in the offline mode via Vicon cameras. Vicon Vera camera is used specifically which are using the optical camera, which are the optical cameras, and making it possible to track and localize the user via millimeter accuracy. A state-of-the-art Vicon motion capture system containing 4 Vicon Vera infrared 1.5 megapixel cameras with sampling rate of 100 Hz, which is used in this experiment. And Vicon data stream SDK, special Vicon tracker version 3.7, is used for constructing the ground truth trajectories. For the localization approaches, we have 5 different localization approaches: the RSSI-based coupled with Kalman and particle filtering, the pedestrian reckoning approach, the RSSI-based fusion strategy, the fusion strategy with PDR-based focus, and the purpose fusion strategy. For the RSSI-based coupled Kalman and particle filtering, a 2D tracking problem is formed with a single user walking within the surveillance region, equipped with 5 different number of BLE sensors. The following nonlinear state space model is considered, as you can see. The initial state of the proposed multiple model algorithm is smoothing the fluctuations of the RSSI values with the KF-based algorithm. After smoothing the RSSI values, particle filtering is issued to estimate the location of the user, which you can see in this figure. For the pedestrian reckoning, basically IMU sensors designed in smartphones consist of 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer. Raw data from the IMU is recorded by the developed Swift application for these projects, which are then fed to the pre-processing unit responsible for the smoothing the accelerometer, gyroscope, and the magnetometer data, and calibration of the magnetometer. As the magnetometer data is a great value when determining the heading of a user in an indoor environment. This unit is considered as a critical step for every PDR-based localization approach. We have adopted least square fitting ellipsoid method for calibrate the magnetometer's raw data. For a random walk trajectory, data set is divided into a small subset for each of which one can determine the heading, which is shown with theta k, associated with the particular step as follows for in these formulas that you can see in this picture, where SL shows the stride length of a user and assumed to be fixed during the iterations. Temp theta k is the orientation of the user estimated from the magnetic signals received from the user's phone. The 2D location of the user, x k and y k at step k is calculated recursively based on the previous location at iteration k minus 1 and phone's orientation at the step k. For the fusion strategies, first we focus on the data received with the fuse RSSI values, as you can see. And then we focus on the PDR-based approaches, as you can see in these formulas. And sigma PDR is the covariance matrix associated with PDR-based estimates, and the sigma RSSI is the covariance matrix associated with the RSSI-based estimates. And the omegas, omega RSI, omega PDR shows the weight which is used to in order to put in this formula for showing the weights of the localization calculation. For final fusion strategy to improve the tracking accuracy, the following final fusion rule is utilized. As you can see, we use two different omega values in order to weight the previous fuse calculated localization strategies in order to use them for have a better estimation for the final trajectory. As you can see, we calculate the final trajectory with the final fusion strategy as it's stated in this formula. And for the results, the mean square error MSC results based on the proposed multiple model fusion framework. As can be seen, the MSC values in meters are relatively small, showing great potential of the proposed hybrid solution. In the third phase of the fusion, which is combination of the RSSI-based fusion and the PDR-based one, the accuracy of the model is better than the standalone fusions. As you can see, we have very better accuracy contrasting with different other approaches, the fusion 1, the fusion 2, and the fusion 3, which all perform better than the RSSI and PDR based approaches. And the fusion third is better than the other two fusion strategies. And as you can see, these are the plots of the movements. For the diagonal movements, as you can see, the purpose algorithm, which is shown in the purple, is better than the other particle of fluid estimates and the dead reckoning estimates. And for the other diagonal movements, as you can see, the outperformance of the proposed algorithm. The other two movements are the rectangular track and the random track. As you can see, the rectangular track, the proposed algorithm is performing better, and for the random, the same results. Aim to prepare the BLE dataset with the precise grand truth for performing reproducible research on indoor dynamic state estimate within IoT application. The paper introduced the IoT-TD dataset and implements a multiple model fusion frameworks to accurately track a user within the indoor environment. They introduced IoT-TD dataset leverage a specific set of 4 optical cameras providing grand truth in indoor tracking with millimeter accuracy. The dataset also contains RSSI values collected from the 5 BLE sensors together with the synchronous IoT signals from the target's mobile device. Furthermore, the paper presents a multiple model hybrid estimate framework which couples RSSI-based integrated Kalman and particle filtering approach with IMU-based PDR via a state estimation fusion. And thank you for your attention.